Okay, 11 o'clock, third Sunday of the month, which means it's time for Chai and Wai from Mukherjee College. Thank you all for coming. Thank you online for watching. But today is a very, very special Chai and Wai because it's the Diwali Chai. So happy Diwali. Happy Diwali. We've done general fireworks, chemistry, all that. We've done many times. So if you have questions on that, please ask me. I'm around. I can answer all the firework chemistry. No problem. But we thought we should have a different Chai and Wai, and we should look big. So we thought of cosmic fireworks, and to tell us about that is going to be Shubhadeep. Shubhadeep Mukherjee is one of our younger faculty members at the IFR, the Department of Astronomy and Astrophysics. He works on cosmology, astronomy, data analysis, gravitational waves, all kinds of stuff. And actually, he's from Pune. Started life in Ferguson College, PhD from Ayuka. Then he went outside, did postdocs at various places, Canada, Amsterdam, etc. Eventually, we could grab him. Please come and get him to TIFR. And he is part of the new efforts that are happening in India. Folks, come in front. There's no mic here, so stop. And he's part of various efforts in India to set up a gravitational wave observatory, which will hopefully be in Ingoli still. And he will tell us about cosmic fireworks. So this is our Diwali special today, fireworks, but slightly different. And remember, online audience, we can get your questions and comments only if you put them in the chat. So please type in your questions and comments. We will monitor the YouTube chat and convey your questions to the speaker. If you're here, please just raise your hand and ask questions. And since you have come, you get something the online audience doesn't, which is you get chai. And you also get a chance to ask questions after the live stream ends. We will live stream only the talk part. After that, it's something extra for all those who have taken the trouble to come here. We'll have a much more friendly, informal session there. Okay, so on that note, let us start. Just in case you want to know about what's coming up, recently the Nobel Prizes were announced, and the sessions in December will be on the Nobel Prize. In fact, we are very, very, very lucky that one of our faculty members, his PhD advisor got a Nobel Prize. So normally we ask our TIFR students to do it, but this time since we have the student of the Nobel Prize winner, we'll ask him. So the next Chai and Wai at the 3 is going to be on the Nobel Prize by Vijay, whose boss had it. Oh, next is correct, sorry. This is December Chai and Wai. Next is November. Oops, sorry. I'm a month ahead. So the next Chai and Wai in November, of course, is topic. It's on chemistry. Yeah, chemistry. So he's the person who does chemistry with lasers and light, and also it's called chemistry between mirrors. And that's going to be in November. December we'll do the Chai and Wai sessions because December is when the Nobel Prize is. So that's when that will happen, the Nobel Chai and Wai. But it's very exciting this year's Nobel, all of them. But as of now, let's go over to cosmic fireworks, and happy Diwali again for all those who came in late. And all those who are online, remember, please put your questions on the chat. So over to you now. You share your screen. Make sure this is on. It's on. You can hear you.
Okay, great. Thanks, Arnab, for the introduction. Right. So, I'm online visible? Okay, perfect. Thank you, Arnab, for the introduction. Also, thanks a lot for coming. Happy Diwali. And thanks to the TIFR Outreach for setting this up on this special day where already are in a festive mood. So as I say, I'm going to talk to you about cosmic fireworks. Please feel free to interrupt me at any point, ask me questions. Of course, after the talk, I'll be around to chat more about cosmic part and how these fireworks that I'm going to introduce you, we are going to talk can more about how we can explore this in the future. So let's start at first with the last word in my title called fireworks. I'm very sure all of us are very well aware of it, right? And the very fireworks, we start with the word start. We start hearing the crackers, right? That's not the only spark. That's not the only story. We also have some fire in action. We see that. Often what happens, you are in your room, you start hearing the crackers going on and off. You go outside and start seeing these beautiful images of that. You start seeing firecrackers by hearing them and by seeing, right? So the part to wonder about is, what about our sky? We see the sky in fireworks, they light up every time. What about the cosmos? This is a beautiful image from our own land, from Hanle, which shows a beautiful image of our sky. And sometimes you all wonder what's really out there in space. To put it in perspective, are there fireworks of very massive explosion where we can see light, we can hear something, possibly like hearing, and start understanding such objects in a completely different way. And this effort is, ongoing. We are in a scenario, thanks to a huge development of technology over decades. We are now in a position to see millions of galaxies, hundreds of millions of galaxies. Soon we'll be reaching out to billions of galaxies. We are seeing. Yes, thanks. Let's do that. So I think now it's good. Okay. So we have seen millions of galaxies. It's a huge development and possibly started helping us, in trying to understand, are there other ways we can see the universe? We often see the sky, right, by our eyes. In some bands, we don't see by our eyes, so we build telescopes. Some things are very tiny, I can't see by my eyes, so I build a very big telescope to see an object very, very far away. So the question comes is, are there other ways to see the universe? Something like a firework, where you see a firework, you hear the sound, you start exploring or you enjoy it by multiple ways. And yes, the answer is, you don't only see things by light or electromagnetic waves, you can also, in my word, seeing, or you can see hearing the universe using gravitational waves. I'll tell a bit more about this, but exactly the way you would think that from very far away a galaxy is bright and I see it, if there are sources of some kind, like extremely large objects, maybe much, much bigger than our own sun, as they come nearby and they start moving, they give rise to waves in the space, as you see on this image. And these waves propagate to you far and far away. And if we can detect this, it's a completely new way and a completely different way to see the universe or to probe the universe. So usually, if you hear about somebody saying, I have a galaxy from whom I can see the light, but if such a galaxy has something like a big two compact objects moving around, then you may be seeing some of these as well. And the question now comes is, well, why do we expect to see such things? Like I have told you about fireworks, and I am now going to tell you about cosmic fireworks. So what do we expect to see such cosmic events? So there are several kinds of this. The way to think about the problem is, if you look out in space, you may find in some galaxy very big stars, much bigger and heavier than our own sun, not alone with a binary pair moving around and emitting gravitational waves and sometimes emit light. So let me show you one such image. It's a simulation which now shows you two neutron stars coming nearby. They are just emitting gravitational waves at the beginning. As they come nearby, they explode and emit a lot of radiation. A truly cosmic fireworks happens. This is what we would expect it to happen from, let's say, from a simulation point of view. What it shows us is that two objects, very heavy, come close by and start emitting gravitational waves and start emitting light too. I can play this video again to show you that you start seeing light not only in visible band in which we see the sky by our eyes. You can start seeing all bands from gamma ray to X-ray to radio and so on. So it's a completely different kind of firework that is happening in the waves. The question comes, how can I detect it? Or can I detect it? What's interesting is that's not the only story. Yes. Few kilometers. They are going to be of the. Yes, that's an excellent point. So, means I have made them extremely dense by making them heavier and making them smaller. So, they become extremely compact objects. Just imagine if I put within a few kilometer size object of mass 40% more massive than sun. It's a completely different game. So typically a mass of the order like 1.4 times the mass of sun is there within few kilometers. And not only one of them, two of them, and they start moving. They start moving, they start coming nearby, and they collide with each other. And that collision gives rise to a firework kind of scenario, where you start emitting, getting light and getting gravity. Yes, exactly. So you can think about a scenario that I have, when I see a sun, it has hydrogen, it has helium, all sort of stuff. Here, this object is so heavy and dense, it has completely squashed by gravity, unless something called as some kind of degeneracy pressure which holds it up. And the object is practically dominated by that. It's a very compact object just before becoming a black hole. Ask me more question about what exactly it is made of. It's a bit technical, but what you can now start understanding, this compact object can emit light and is going to emit gravitational wave if they really start colliding with each other. Okay? And this story is not only for neutron stars. Even if I give you a neutron star and black hole, this thing will happen. I will play this movie again. Here you are seeing one of these that he was asking about neutron stars. Other is object which is even more dense. An object which is even smaller in size and even massive than sun. When they come nearby, they will also start emitting gravitational waves and sometimes radiation. Much more radiation than what we see and it gets from sun and becomes this hot. It's a lot of energy that gets emitted. Okay? And such events can also be there for black holes. Here you are seeing a simulation of two black holes coming nearby, and the entire space is squashing around it, emitting a tremendous amount of energy in form of gravitation. These are the biggest bangs happening since the Big Bang of emitting a large amount of radiation to the sky. And if we can detect them, they are possibly the biggest fireworks happening on the cosmic world pretty frequent. So the question now comes, how do we detect? I mean, how can we measure this thing? Something very far away is emitting light and emitting waves in the space, which we call the gravitational waves, which is propagating. How can I detect this? And this particular effort is been made possible for the very first time. Just give me a minute. I'm trying to show you a video. For the very first time by the LIGO detectors in collaboration with Virgo, exactly 10 years back. 10 years back, for the first time, we could detect gravitational waves. And that's the concept which measures the tiniest length change in the on ground ever possible. It measures something like 1 part in 10 raised to 21 in length. So if you change the length by 1 part in 10 raised to 21, this detector can measure it. You have a question for me? Yes, exactly. It's few times to few tens, few hundred times the energy in the sun. The entire galaxy becomes extremely bright. So it's a amount of energy which is thrown away is more than the amount of entire rest mass energy of the sun itself. So it's a completely different scenario where these collisions starts emitting light and gravitational waves in the space-time. Absolutely, thanks for bringing this up. But what's really becomes challenging that this large amount of energy coming from very far away makes the signal extremely weak. So weak that that a length, like if I give you my mobile and a gravitational wave is passing through it, this mobile will change by 1 part in 10 raised to 20, 1 part in 10 raised to 21. Just imagine, it's much thinner than my width of my hair, or possibly many things you can imagine. The smallest length change is able to measure by seeing a small change in the wave of the light, which is present in the detector, by a technique called interferometry. I'll explain this more, but what's really becomes interesting that this effort of trying to detect the signal when gravitational wave is passing between them, the length changes a little bit. That little bit change in the length makes it possible. I'm having a struggle in playing the video. Just give me a minute. So that when this light propagates, this particular arm starts shaking as gravitational wave passes through it. So that means if I put a light here and a mirror here, if there is no gravitation, there is a length of this room. But if there is a gravitational wave, the length of the room will change tiny, and it is happening. I can't see it, I can't feel it, but I can make a detector which can feel that and detect it accurately and give me a scientific output. And that's what has been built up. I'll tell you how our current effort from India is going on to get a detector of this kind in our very own land in Mumbai. And this particular effort makes it possible to detect these events I told you, these cosmic fireworks, happening very far away. And this entire effort has been possible for the very first time when exactly 10 years back, we started seeing something coming in the detector, which is like a chirping behavior. Something which time the frequency is changing, like a bird is chirping. That's the extraordinary signature of gravitational wave. This specific nice property of frequency and time evolution. Well, is it happening only in only one detector? We have multiple detectors. We have two independent detectors which have seen the same signal and started trying to ask, okay, what is producing? What we have discovered for the very first time, two objects of around 30 times the mass of the sun is moving and coming close to each other and emitting gravitational wave, which we start seeing. It's a wave, it's an oscillation. So you see those oscillations over here, cycles, as this object starts coming nearby, they touch each other, and after that there is hardly anything released. And this entire effort start getting recorded by those detectors I told you, which measures tiniest change in the length. Just see the y-axis over. This is the amount of change in the length you see. And that's a few 1.10⁻²1. Please go ahead. Yes, exactly. Very good. Yes, so the in language, yeah, so the question is it a perturbation in the space-time metric? Absolutely. So gravitational wave induces perturbation in the spatial part of the signal, of the metric, which we try to measure. And when we do this by building a detector which can measure distortion or deviation in the space, it gets imprinted in our detector by changing the metric as you mentioned. More questions for me? Well, if that's the story, let's try to understand what's really happening. Two heaviest objects coming close to each other and emitting a lots of radiation that you are detecting. Let's try to get a physical view of this entire scenario. That's the signal that we have seen. Something in LIGO Hansen and LIGO Livingston, where two black holes as close as 30 times the mass of the sun starts coming close to each other. This is a simulation. This is not, we cannot resolve these objects directly. We see them in our detectors, gravitational. As they come nearby, they collide and they become a single black hole of even heavier mass. So we have detected black hole, we have detected black holes and emitting gravitational wave and producing a black hole afterwards, as far as we know so far with our data. And this is what happens as two objects come nearby. They start coming nearby, they start moving faster. As they start moving faster, they emit gravitational wave of higher frequency. And that wave starts propagating from a very far away galaxy to us. It gets weaker. Just imagine, as it reaches Earth, the entire Earth starts moving little bit. Very tiny, this is a very accelerated image, but this is what is really happening. The Earth is shaking because of this huge wave. It's like, you remember, like when you hear the sound of a firework from a cracker, it's exactly like we are hearing the universe through gravitational waves. And those waves comes to our detector, starts shaking it. It's shaking like a wave, and I start measuring tiny change in the length by seeing how the two perfectly, very accurately known light of source would get to some interference pattern of constructive interference or destructive interference, and it starts showing up in my detector. So I start seeing a little and tiniest change by seeing the change in these phase shift, as you can see, whether they are matching or they are not matching. If they start matching, I start with a beautiful source of light, and if they are not matching, I don't see. And this is my way to measure the tiniest change in the length of the universe using lasers. And this is so small that it's smaller than the size of an atom. It's smaller than the size of a nucleus. It's a tremendous effort in measuring tiniest change possible. So, going back, this is the source we are studying. And you now want to understand what's really giving us all this. So we start becoming a scenario where we now have objects very far away emitting tons and tons of energy, and we can see them. But the question now comes is, how far can we see? And then question comes is, if we see them, what am I going to learn from them? Let's take a look at that. This particular result is showing you our effort in able to go further out in universe. This circle means how far I can see. More with the beta detector we are proceeding, now with O4, we are able to see much further away, about 160 to 190 megaparsec, which is at a cosmological distance. To give you some perspective, our galaxy is only about few tens of kiloparsec, about 30 kiloparsec. It's a completely different size when you go to megaparsec, and now we're talking about few hundreds of megaparsec. So we are right over here. There are many galaxies, many clusters in this image, and we can see gravitational waves from them using our detector. Okay? And how many did we see? We have already seen about 170 of them, and this is how all of them look if you make a GIF or simulation of that. Objects of very different masses are emitting gravitational waves at a cosmological distance, very far away. So you now know black holes in our forms, they emit gravitational waves, and they can sometimes also emit light if there is something special about them or something special around them. Ask me this question later during the chai part of chai and wine. But moving on, are there other kind of cosmic fireworks that we have seen? And the answer is yes. I started talking about binary neutron star. In the year 2017, we had the first time to detect gravitational wave and electromagnetic signal together. This is gravitational wave. After about 2 seconds, 1.7 seconds, we start seeing a blip in the gamma ray. You remember this video I was showing you of this video I was showing you about two neutrons are coming to each other, very near to each other. When they are here, they emit gravitational wave. That's the part which we saw. And as soon they start touching each other, they start emitting radiation in the extremely high energy, in the gamma ray. That's what has been seen. And soon after that, multiple telescopes start seeing the sky in all other bands, not only in visible, but in all other bands. Starting from X-ray, from UV, optical, infrared, up to radio. And this line tells you when all this has happened. What it tells you that about 2 seconds from the gravitational wave emission, as soon the gravitational wave emission happens, a lot of energy emitted in gamma ray. Followed by that, I start seeing the bright, nice light in optical, the band in which we see the sky. We started seeing in infrared, we started seeing in X-ray, we started seeing in radio. A truly cosmic firework, where like you see a firework where you hear things, and you see the lights from it. But instead of just a light invisible, now you have firework from gamma ray to radio, and here gravitational waveform. And this enormous effort has made it possible for us to understand how, yes, yes, I will come there. Yes, I will come there soon. I told you we have seen them. I told you how we see them. Now I will try telling you what are we going to learn from them. How that thing we have learned is going to come to our very daily life. Exactly as Arna pointed out, you will soon learn that this massive object that has collided with each other is the potential place from where many of our favorite metals start coming, which includes gold. Okay? Let me take that up later a bit. I'll tell you now what's inside, what's going on. Two objects, here you see them in their matter, since we see. And here you see that their energy density in gravitational waves. Two objects start emitting a lot of gravitational wave high density in this region. They go down as you go far away, which is shown by violet or blue. And as this matter starts clashing with each other, it emits all sort of lights. Is only light? The answer may be no. It may be also emitting something else, such as neutrino. We are yet to detect neutrino from these kind of sources. But the question is, possibly they are happening, and in future, some of you may be a part of it, will detect neutrino from this kind of sources. Moving on, what I now tell you, that's exactly he was pointing out, that this enormous firework which is happening in the sky has taught us several things. It tells us a way to understand how far the universe is expanding. Today, it tells us what is there in this exotic object I start with, called neutron star. What's really there inside? When these two objects starts hitting each other, in some sense they are breaking. So many of us, our kids, and even now, we start breaking things to know what's there inside. Nature is doing that for us by breaking the neutron star, and we can detect them. We can also start seeing how elements, metals, called as those metals that are not produced in early universe, are produced. And we have, for the very first time, have evidence that metals like gold are produced by neutron star mergers. So we knew it, we hypothesized it, but we have now found scientific evidence that's the case. And from these areas of understanding how metals form, how neutron stars form, to understand how these objects itself have formed, how this astrophysically I would expect these big objects to form. And these are the several efforts which are going on in trying to understand the physics from these objects. Yes, please. Butter? Oh, excellent. Very good. So like I told you, so the question is, what are neutrinos? So I told you about gravitational waves. I told you about light. There can be some other messenger which gets emitted from this source. Neutrino is one of those. You learn that sometimes neutron to proton reactions can happen, and it can emit some amount of neutrino, something extra which I can detect, and we have detected them. We have never detected those from these sources, but we expect them to also emit a lot of energy in these neutrinos. And yes, there is another kind of messenger, another way for us to see the universe. Thank you for the question. So, taking that and now taking a step towards what kind of discoveries are we making from this cosmic fireworks? What are we learning from this? One thing we have started learning is how fast the universe is expanding. This may not be a new thing, right? How many of you have heard before that the universe is expanding? Yes, all of you. We need to measure how fast it is expanding. And gravitational waves allows us to measure that for the very first time using a multi-messenger way, in which a cosmic firework tells us how to measure so-called the Hubble constant of the universe today with a nice accuracy and precision, which in future is going to improve significantly. For the students, this is a result which is obtained by one of the master students who worked with me, Harshang Nimankar from St. Xavier's, who has obtained this way of saying us how well I can measure the expansion of the universe in future with gravitational wave detectors. And in particular, what it tells us that as I have more number of sources, this is the x-axis, I am going to get to a measurement of the Hubble constant to a few % level in the coming, let's say in coming decade, when LIGO India will be operational. Not only that, there is something even interesting we can explore. We know universe is expanding. Do you know that universe is also accelerating? It appears that it's not only expanding, it's also expanding faster every day a little bit more than the other days. So universe is accelerating. And yes. Yes, no, so Hubble constant is the value of the expansion rate today. What really increases is the Hubble parameter. With time, this value, the rate at which it is expanding, is going a little faster every day. So yes, if it is the expansion rate, that rate is going up. Very tiny, 1 part in a billion, close to that, or even less, but it's a tiny change for happening that I would like to make. So you can, and what's the beautiful thing happens with gravitational wave, I can start, this is what one of the efforts going on at PIFR, or we start understanding how well we can infer, we can measure this acceleration of the universe using gravitational waves. One of the things which none of us understand is the acceleration of the universe is possibly happening by a hypothetical term called dark energy. And we can possibly go and measure dark energy, its equation of state using gravitational wave in the near future. There are also other efforts going on in measuring it. It's a combining several efforts together to get to a measurement of the dark energy. I told you about cosmic fireworks. When we make fireworks, we throw something, it goes to the sky, it becomes bright, we see a bright light from it. What about these fireworks? How are they really forming? How are they emitting gravitational wave in our lifetime? This is an open question about how heavy and how early these black holes form in the universe. And thanks to gravitational wave observations, we are now able to go to an area where we can now start asking this kind of questions. Not only one black hole, now we have many black holes. You can try to understand how universe cook black holes, how these black holes are forming. This image is made by a first-year student from the gravitational wave data, telling us how heavy objects are present on the y-axis and how far they are in distance in the x-axis. This is a way for you to understand that how heavy and how early these black holes are forming and how far they are from us. And this entire list has become even bigger. We now have several sources as a function of distance from us. I can start measuring gravitational wave sources or black holes of very different masses. So this m dot over here is your solar mass of sun. And just imagine these objects are of masses 100 solar mass. Just imagine you have an object which is 100 times heavier than sun, exists in the form of black holes, means much heavier but much smaller in size, few tens to few hundreds of kilometers, much smaller in size. And I can go and measure them using gravitational waves, and I have seen them. Because as they move towards each other, they make a tiniest change in the length that I can go and see using my detectors. And this particular effort has made it possible for us to quantify the properties of the black hole. Like I said, different kind of stars, right? I have HR diagram where I say, star is very bright, star has a very high temperature, how it is more, how it looks. I can do the same for black holes now. I can start drawing for the very first time how heavy these black holes are. Are they spinning? Are they very far away in the universe? All these properties of the black hole we start measuring. A very interesting part of the black holes is that it's a very big but very simple object to quantify. If you know its mass, if you know its spin, and if you know its charge, you can quantify the black hole perfectly. And with the help of these observations, we can measure whether the black hole is spinning and how heavy they are. Okay? We have now started also going to the physics questions. Started asking something a bit even more deeper and toward how these black holes are forming in the universe. Are these black holes evolving with time? Are their masses evolving with time? This plot is a plot made by a student or as a function of different black hole mass in the x-axis, and the merger rate plot per black hole means how many black holes are merging in certain mass range as a function of their distance from us. And what we have started seeing, there may be some mild evidence of evolution of black hole mass. A completely new research frontier which is now started coming up, which tells us that there may be not only black holes, a few of them, there are underlying physics which tells us how these black holes are going to be evolving in the cosmic history. Okay? And we start measuring, this is one of the very new results, we start showing us, is there any deviation of the black hole distribution if you don't consider it to be not evolved? If you consider it to be a non-evolving scenario, do you see any evidence of it to be evolving or not as a function of different masses? And we start seeing some hint on this. So ask me a lot of questions later. I understand this is a bit technical side, which tells us a lot of different measurements has gone in to get a neat physics answer of are the black holes at any cosmological distance have similar mass or mass properties on it. And possibly you are going to see may not be the case. Moving on, gravitational wave is the aspect of gravity. Two objects comes very nearby, very heavy, start emitting gravitational wave. But there is another new and interesting aspect of gravitational wave and gravity, which is gravitational lensing. Both of them are effects which is predicted by Einstein's theory of general relativity. If anything is heavy, it will bend the space-time. So light will get lensed. How many of you have seen a lensed image of a galaxy? Some of you, excellent. Similarly, we start seeing lensed image of gravitational waves. This is for the very first time possible, where one can start seeing images of very heavy objects around which when gravitational wave is coming by, you start seeing lensed gravitational waves. We are yet to discover it, but this will be the first of its kind, which should be there if Einstein's theory of general relativity is right. And the very interesting part is this particular aspect will tell us what kind of lens is causing this kind of images I see from a black hole before lensing and after lensing. And we have made this observation from the current LIGO data. We are able to make for the very first time inference of lensing signal. We haven't found anything yet. It's still yet to be discovered, but we know as we keep on searching and our number of events goes up, we should be able to detect for the first time the gravitationally lensed gravitational waves. Moving on, this is all about told you about the current ongoing ground-based detectors. We also have an effort of detecting gravitational waves from several other bands. So in this cosmic fireworks of big objects coming close to each other and emitting gravitational waves happen, these don't only happen in the frequency range I can see from LIGO, which is at an extremely large frequency over here, but it can also happen from a very low frequencies, and this is showing you the possible spectrum of gravitational wave that is possible to achieve from the upcoming detectors. So like light is not of a single frequency, right? From radio to gamma, I see light at all different frequencies, the entire electromagnetic spectrum. Similarly, gravitational wave come in its own spectrum, from very, very high frequency to low frequencies. Like I have seen signal at the ground base from LIGO. I have told you LIGO-Virgo collaboration. We have also started seeing something in this nanohertz range. Right over here, around where the signal or the frequency is typically 10⁻10 times lower than what we see in light. The frequencies here are of the order 10 hertz, here of the order 10⁻⁹ hertz. It's a completely different window. Excellent. Yeah. Yeah, excellent. That's right. So these are the time periods in milliseconds. These are in time scale of years. Exactly. So think about a gravitational wave which time period is of the scale years. It's a completely different regime for us to detect it. But how can I detect it? Like I told you here, from ground-based detector, such large wavelength and cannot be detected from Earth, but using something else as a detector. And we use pulsars to detect. What do? We start measuring radio signal from pulsars which are in our galaxy, and those pulsars act like a detector for us. We measure tiny, very tiny change in the pulses of these pulsars with time over many of them in the sky and try to infer the gravitational wave signal from that. And this effort has also been possible thanks to the pulsar timing array and also a significant contribution has been made by our very own Indian director, GMRT, which is of NCRATIFR. And what can these objects tell us? We can now start, instead of talking about few tens or few hundred solar mass black holes, we start seeing black holes of billion solar mass, a billion times the mass of the sun, which are sitting possibly in the centers of biggest galaxies that we see. And yes, this effort has been enormous. We are now in a scenario to try to understand, explore the host of these massive black holes, which are possibly detecting through gravitational waves for the very first time. Where these black holes form of billion solar mass, how their galaxies look, and what is the connection between the galaxy physics and galaxy growth, galaxy's evolution with these black holes. And this is now possible by, we are in a scenario to try to model, try to infer this from gravitational wave observation, from coming from cosmological scale, which is billions of parsecs, to sub-parsecs, much smaller. Or in simple words, we are talking about scenarios of black hole size objects where understand the physics at a cosmological scale, which is billions times larger than anything of the black holes. And this is the physics that we are trying to understand from black hole galaxy connection. And this is an ongoing research which will tell us soon, the upcoming detectors as well, that how black holes in the universe starts going. This image in the right is showing you how black holes and galaxies are possibly connected, and what kind of signal I will be getting in the coming years, which will tell us the interlinked connection between these. I will now start going to the end of my talk. I think I have a few minutes left. But I will talk about the future prospect of astronomy in using gravitational wave science. So I have shown you about this particular spectrum of gravitational wave from extremely high frequency to very low frequency. And there are several ongoing efforts going on to see signals in many of these bands. Like we see electromagnetic signal or spectrum with different detectors in different bands. We need a similar way to see the cosmos using gravitational wave by detectors of very different kinds in different bands. So at the largest scale, or the smallest frequency, we will see gravitational wave by cosmic microwave background. Topic in its own, which is a tiny fluctuations on the sky temperature, and we can measure the polarization of such signal. Ask me a lot of questions in the after the talk. I'm happy to answer. But there are ongoing efforts internationally to detect this signal. In the very near future, we have already having pulsar timing array. This will be advancing by order of magnitude with the help of the next generation radio antenna called Square Kilometer Array Observatory. India again is a part of this. And we will be able to explore the sky using gravitational waves in the nanohertz range, in the range where the signal length period is of the order of a few years. Moving on, I will now come to a scenario of this part where it is the millihertz range. This is a signal which we can detect from the space-based gravitational wave detector, which we call as LISA. It's funded It's an extraordinary mission which will track Earth of arm size 2.5 million kilometers. So just imagine that LIGO scenario of 2.5 million kilometers big, going behind the Earth and circling the sun for years. This particular effort will make it possible to detect black holes of millions of mass. So I told you about billions solar mass. I told you about millions solar mass, means million times the mass of sun. And at the ground base, as I started with, it will be of the order of a few tens, few hundreds of solar mass. And that's the place where our future detector from India, LIGO India, is going to be built. It's a new detector which is going to see the sky with along with the global effort of 2 LIGO in the US, Virgo in Europe, Kagra in Japan, and LIGO India in Ondha in Maharashtra, which is now funded by the government of India, with an expected timeline of commissioning by the end of this decade or early next. So that's the geographical location. Anyone of you can go and find it. That's the artist's impression and of LIGO India site. And we expect to not only be able to do astrophysics of all different kinds, but we are going to have impact and scientific discoveries with a large amount of electromagnetic observations, neutrino observations, and science is going to be impactful from fundamental physics to our very own daily physics, appearing in our to the extent of science outreach through our textbooks. And to give you some kind of timeline, this is the story of 2015, and we have started here. Right now, we are at our 4th observation run, around 2024, 2025. We are going to start in a year or so with the next observation run called 05. And LIGO India will eventually be starting soon after that. That's the plan, with all 5 detectors starts operation. And never forget that this story is going to be pretty incomplete without the entire firework, where you want to hear things, you want to listen things. And the listening part is from gravitational wave, and the seeing part is coming from several telescopes operational across bands from radio to gamma. So a coordinated effort between gravitational wave science telescopes, neutrino telescopes, and electromagnetic observations are going to be one of the key ways to see these cosmic fireworks. And I will end my talk here. I'm presenting on behalf of my group, which works on gravitational wave, and we are part of several of these national and international collaborations to detect gravitational wave. And most of the results I have presented to you as coming from my group members, who are from PhD students to some of the undergrads from colleges in Mumbai or outside. And this particular story, you can be a part of it. If you would like to know what cosmic fireworks are going off today, are we detecting a black holes today or not, there is an app which you can get in your computer, laptop, or in your mobile to get an alert of black hole merging, neutron star merging, or neutron star black hole systems on a regular basis. Also, what I always find interesting is this entire effort of scientific development through discoveries which is happening by advancing in technology is a science for all of us. And it's equally true that all of us are for the science. So whether you are from school, high school, undergraduate program, you are in graduate school, or you are a researcher, you can contribute to this science at all different levels. At my group, we have started that if you are at high school, you are at an early career of your first year or second year of your undergraduate program, you can join and start learning some hands-on activities, some how to get to from a basic physics understanding to get a concept of astronomy through some calculations, some experiments, and so on. We call it something like a yoga program, the Young Scientist Astronomy. We have several short-term and long-term projects which are funded by several government sources, funded by TIFR. While when you are a second year or third year student in undergrad, you're a master's student, you can do several kinds of internship, including master processes. We have an excellent integrated program and PhD program where you can join us and work on the research frontier. And of course, from graduate student to researcher, you can work with us as a postdoc, you can work as an engineer in both software side, in the both hardware side, and of course, citizen science. The several aspects where you all can contribute towards the citizen science programs, which are also operational by several bodies in the country. With this, I think I will end my talk saying that let's look up and discover the cosmos with your favorite messenger. Maybe gravitational wave, maybe cosmic rays, maybe light, maybe neutrino. And with this, I'll end this talk saying that thanks a lot for you to coming and best wishes for the festival of hope, prosperity, and joy. Thank you.